We'll see an example for this considering a simple MH sampler for drawing from the target distribution that is the standard normal distribution. Like before, this is actually a toy example that does not involve Bayesian inference. So here we just apply the MH algorithm we introduced last week to generate from target distribution that is normal 0, 1. For MH algorithm, we need to specify a proposal distribution. And in this case, we will use y given xt follows the normal distribution with mean xt and variance sigma squared. And when we calculate the r hat, we need to specify what kind of summary statistic we need to use. So what psi we decide to use. So for this example, we will use psi, that is the sample mean of the draws. To calculate r hat, we will write a function for computing it, taking a matrix of size as the input. So this function is called Gelman-Rubin. It takes psi as the input and outputs the r hat. Psi is a matrix with a total of k rows. K is the number of chains, and n columns, where n is the number of MCMC iterations. The ijth entry of this psi matrix is the psi statistic calculated using the ith chain, using the x draws from the first iteration to the jth iteration. And each row of this matrix is a chain. And each of them have different starting values. First of all, let's convert psi to a matrix in the case that it isn't yet. N, which is the number of MCMC iterations, is the number of columns of psi, and K, the number of independent chains we generate, is the number of rows. We will first calculate the between sequence variation, B. In order to do that, we need to first obtain what is the average of psi in each of the separate chains. This can be obtained using the row means function. It will calculate the mean of each row of the psi matrix, and each row is a chain. The B, which is the between sequence variance, is given by n times the variance of the psi means. Next, we will calculate the within sequence variation, W. In order to do that, we need to first get the variance of each of the chains. We can do this by using the apply function on the psi matrix, and we calculate the variance of each row. So by doing it for each row, we specify margin equals 1. The result will be a vector psi w, where each entry is the si squared for that particular chain. And then our w will just be the mean of the psi w's. Once we get the b and w, we can get our var hat. And that's the weighted sum of the w and the b. And dividing that by w gives us the r hat, which is the Gelman-Rubin statistic. Okay, let's go back to our example where we try to use MH to draw from normal 0, 1. Let's create a function that's called normal chain. It's going to obtain MCMC draws where the target distribution is normal 0, 1, where the inputs are sigma, which is the standard deviation we use for the proposal distribution, n, the chain length, and x1, the initial value. This function first creates a zero vector with a total of n entries. This is for storing the MCMC draws. The first entry will be set to be equal to x1, the initial value that we input. We'll also create a u vector, which is for doing the acceptance rejection test. For each subsequent iteration, we will first generate a y from the proposal distribution, which is the normal distribution with mean xt and standard deviation sigma. And then we will calculate the acceptance rate, which is given by the ratio between these two. If our uniform sample in the ith iteration is less than or equal to this acceptance probability, we will accept and set the next x to be equal to y. Otherwise, we will reject and the next x will be equal to the current one. At the end, this function returns the entire chain of x's, which are the MCMC draws that we have obtained. To evaluate convergence, we want to generate 4 separate chains, in other words, k equals 4, with different starting values. For each of this chain, we're going to implement the MH sampler with the same proposal and the same target distribution. However, the starting values are really far away. For the 4 chains, the starting values x0s will be -10, -5, 5, and 10 respectively. And for simplicity, we will just use a proposal standard deviation of 0.5 for this example. Let's do a total of 15,000 MCMC iterations for chains, and we'll specify a b equals 1,000 over here, indicating that later on when we create plots and other things, we want to toss away the first 1,000 draws. We'll create a matrix X with k rows and n columns to store all of the draws. And x0 are the initial values for each of the independent chains. In the ith chain, we will set the ith row of the X matrix to be the output of normal chain, where we implement the MH sampler with proposal standard deviation 0.5, chain length 15,000, and initial value given by the ith entry of the x0 vector. So you can see depending on the chain index, the starting value will be different. The starting values are really far away for these 4 chains. Our question is 15,000 iterations sufficient for all of them to get to somewhere close to the stationary distribution or the target distribution normal 0, 1? Okay, so to determine that, we need to calculate the r hat. And to calculate the r hat, we need to first get the size. The statistic psi ij is the mean of the x's in the ith chain from iteration 1 to iteration j. So for a particular chain I, psi i1 all the way up to psi in can be obtained by taking the cumulative sum of the xj's divided by 1, 2, 3, all the way up to n, respectively. Here's the code for implementing this. We first create a matrix called sums, which calculates the cumulative sum vector for each row, in other words, each chain of X. And then once we get the cumulative sum, we need to divide it by the sample size, which is the chain length up to that particular point. So we'll create a matrix called psi, which is the sums matrix divided by 1 through n. What this will do is it will divide each column of the psi matrix by 1 through n. And because at this point, after using the apply function, the psi we get will have a total of n rows and k columns. So you can see we transpose the original X matrix. So we want to transpose it back to have k rows and n columns instead of n rows and k columns. So we'll set psi to be equal to the transpose of psi. Based on this, we can apply the Gell-Mann-Rubin function we created to calculate what is the r hat in this case. For this particular example, we got a Gell-Mann-Rubin r hat around 1.08. R hat is less than 1.1, suggesting convergence. In other words, although we started at really different places, after 15,000 iterations, the 4 chains got to similar places. In other words, the stationary distribution. We can take a look at the 4 chains chain plots. Here we'll toss out the first 1,000 iterations. And the method for plotting the chains is the same as before, where the x-axis is the iteration index and the y-axis is not the corresponding x, but instead the corresponding psi, the average computed up to time x. up to time j. And here are the plots. There are 4 plots, and each of them is the chain plot for each of the 4 chains. And the 4 chains have different starting values. You can see that although we toss away the first 1,000 iterations, the 4 chains all started at quite different places. However, it appears that at the end, when we get close to iteration, say 14,000 or 15,000, each of them have stabilized, and the stabilized value is somewhere around 0. And recall that 0 is the mean of the target distribution. The target distribution is normal 0, 1. Very often, we will want to generate a convergence plot which describes the progression of the R hat statistic as we increase chain length. This can be done by incrementally increasing the chain length and computing R hat for each of the possible chain lengths. Here's the code for implementing this under the current example. We will first create a vector called R hat, and it will have a total of n entries. Each of the entries will be used to store what is the R hat if we just run so the jth entry will be used to store what is the corresponding Gelman-Rubin R hat if we just run the chains for a total of j iterations. So we won't do it for the burn-in, so the first 1,000. Starting from 1,001, for each j, we will compute the Gelman-Rubin R hat only using the size from time 1 up to time j, instead of using the size all the way up to time n. So the resulting R hat vector, the 1,000th to the 15,000th entries of this vector, will contain the R hat for each of these possible sample sizes. And then we can plot it where the x-axis is the chain length and the y-axis is the corresponding R hat statistic computing at that chain length. We'll also include a dashed line at 1.1, indicating the threshold of 1.1. So here's the convergence plot. You can see as we increase the chain length, the R hat value in this example stably decreases. At around 12,000 iterations, it stabilizes to something that's below the threshold 1.1, indicating convergence. So what it means is that for this particular example, running the chain for 12,000 iterations is perhaps sufficient for us to reach the stationary distribution. So what you might want to do is to set the burn-in length to something around 12,000. And you use all of the iterations beyond 12,000 as the post-burn-in draws for doing posterior inference or to compute all sorts of summary statistics. For this example, we calculated R hat from scratch. An alternative to this is to use the CODA R package. We're not going to discuss how to use it over here, but you'll get a chance to look at it in homework 5.